week 4, Tuesday, and we are going to look at centric symmetrical bending, and we're also going to look into centric unsymmetrical bending. So as you all can recall, centric or the term symmetrical bending is related to the stress field distribution. Okay, it's nothing to do with how the structure is loaded, what is the geometry, but it's more on looking at how the stress field has been distributed. And on symmetrical bending, usually the bending moment only acts on one axis. Okay, so just the general formula. So if I were to draw my transformation, I'm going to sketch this in 3D. So if this is X, this is Y, and this is Z, okay, and this is our structure over here. And I'm going to roughly sketch out the position of the centroid. This is just a sketch of the centroid. Okay, so this is a position of the centroid. So in centric symmetrical bending, the stress in the X direction can be equal to my over Iyy multiplied by Z, or stress X is equal to mz over Izz multiplied by Y. So the moment is only applied in one axis. What do I mean by one axis? So the moment can be applied so it can be either moment in Z, okay, so when you use the right hand rule, this is your moment in Z. Okay, this is the this is the arrow, or it can be moment in Y. So I'll write down here, or it can be moment in Y. And again, we use the right hand rule. It'll be going down this way. Okay. So this is for centric symmetrical bending, and I'll write this now. The moment can only be applied in one direction only. Okay, you cannot have both my and mz. That is unsymmetrical already. You only can have moment in either m, in y, or moment about z. Now, the next thing I'm going to do is I'm going to sketch the stress profile, the normal stress profile. Okay, so we are talking about normal stress profile. Okay, so if I have a structure, this is X, and this is Y, and this is rotation about Z. We have a beam. Okay, and one side of the beam is pin, and the other side is a roller. Okay, so just to make sure that what we mean by pinned. So in pinned, x displacement is equal to 0, y displacement is also equal to 0. When you have a roller, what it means is x is not equal to 0 because the structure can move left and right. There's no restriction. It can move left and right. However, it cannot move up and down. So for this case, y is equal to 0. Okay. So usually when we don't allow movement, there is a reaction. So for this case, force in the x direction is not equal to 0. Force in the y direction is not equal to 0. So we are talking about reaction. So the reaction force in the x and y direction cannot be equal to 0 because we are restricting moment. However, if the structure is pinned, fx, okay, is equal to 0. Why fx is equal to 0? Because x displacement is not equal to 0. I.e., you allow the structure to go where? Left and right, left and right. There's no reaction. However, on a roller, y is equal to 0 means y displacement is equal to 0. So reaction force at y is not equal to 0. Okay, I hope you all can remember this. Okay, and then if we have a load applied at the center, and this load is our Py. Okay, so how does the normal stress distribution look like? Okay, so now I'm going to draw our cross section view. So now I'm going to change my transformation now. So now we're looking at the cross section view. So this is our y, this is our z. This will be rotation about x. Okay, so now this is our cross section view. Okay, so this is our cross section view. And over here is our centroid. Okay, so this line I draw is our centroid. So when that is the case, okay, when that is the case, I'm going to draw the normal stress distribution. So to sketch the normal stress distribution, you know Py is acting from the top. So at the top, at this surface, it'll be under compression due to bending moment. At the bottom will be on tensile. Okay, so if we're going to sketch the normal stress distribution, how would it look like? Okay, so if I'm going to now have one axis over here. So this is our normal stress in the x direction. And I'm going to draw a vertical axis. So this is stress y, right? So as you can see on the right hand side over here, they are all in tensile. At the center is 0, that's for sure. Sorry, it was stress y. See, y displacement is not stress y. I do beg your pardon. Okay, and then if the left hand side from the 0 is normal stress in compression. So on how our structure is loaded, what we have is this. Okay, so I'm going to draw the stress profile, the normal stress profile. So this is the normal stress profile. So you ask me, Eugene, where are we drawing now if we view it from our XY structure or XY transformation or XY plane? So if I'm going to sketch the same line, okay, it looks like this. Okay, it looks like this. Okay, so I want you to visualize this face as the material that I'm highlighting in orange now. Okay, so this is the same face. This is where the material is. Okay, and then when it's compression, you draw the arrow like this. Okay, so it's pressing towards the what? The yellow line or the material. Okay, and then in tensile means the yellow line is where reference where the material is. You're pulling it away. Okay, you're pulling it away. Okay, so over here, what we have is we have a specific stress S value, and or I call it, this will be tensile stress X and minus Y, and over here will be minus stress X, and you have positive Y. Okay, so this is how, so when the arrow point towards the material is compression, and when it's pulling away it's in tensile. Okay, so that's how we sketch for centric symmetrical bending. So this is classes. So I will write this out. Okay, so hold on, before I go on, if you look at the stress field over here, at a point which I'm drawing a dot now, this point, right, is known as the neutral axis. So on the neutral axis, stress X is equal to what? Is equal to 0. Okay. So something very interesting occur down here. And what do I mean that something very interesting occur down here? So under symmetrical or under centric symmetrical bending, the position of the centroid centroid is the same as the neutral axis. Okay, remember the centroid position is determined from geometry, okay, whereas the neutral axis position is determined when the normal stress X is equal to 0. So one is determined by geometry, the other one is determined by stress field. Now I will show you now a situation where the centroid and the neutral axis are not at the same position. Okay, I repeat again, I'll show you another example where the centroid and neutral axis position are not the same. So why is that so? Okay, so then this can happen when the loading is done this way. So now if we have a beam that is built in, okay, so our beam is built in, which is different from different from just bending about one axis. Okay, and then we now, so I'll draw transformation again. So this is our X and Y, and this will be rotation about Z. So now we have a force, okay, acting at the free end.